Good afternoon, ladies and gentlemen. Welcome to the very first episode of Maths with Gary. So basically this is my YouTube channel. I'm going to put up some videos on topics of maths that I either find interesting or am teaching. And I'm making them available to everyone. So if you find them useful and helpful, please post a comment. And if there's anything in particular that you would like to see, you can feel free to do that too, although I'm not making any promises. So I teach maths at a couple of places, and it's first year engineering maths. And so most of my time is going towards that. If I get time to do other stuff, great. If not, then that's really a bit unlucky for you. But anyway, so this first episode is about testing a subset to see if it's a subspace. Now, a subspace is a small set of a much larger set of objects that may or may not be vectors. They don't have to be vectors. But the very first spaces were of vectors. And so we still call them a vector space today. Even if it's matrices or polynomials or something like that. And they can all be vector spaces, even though they're not really vectors. But what that means is they obey the same laws as an actual vector space. Now, a subspace is a smaller set of that obeys two further laws, and those are closure under addition and closure under multiplication. And I actually want to share my file here. I want to share my file, which is this one. Here we go. So this is all sort of introduction, and I'm not going to bother about the full set of laws because we're only concentrating on subspaces. And so certainly I wouldn't be setting any questions for my students that say, is this a subspace, when in fact the set that it's a subset of isn't even a vector space. That would be a little nasty. So there are two tests for a vector space. One of them is closure under addition, and I should mention that I'm using the vector notation here for convenience. Even though these things U and V may not in fact be vectors, they might be matrices, they might be polynomials of degree less than or equal to something, 2, 3, whatever. I'm not using the bold for vectors because I can't do it on the board. I see no point in using something in print that I can't do on the board or when I'm working with students with a pen and paper. So I will be using this notation of these little twiddly things underneath, which is a little old-fashioned these days. I am pretty old school. I think this is a good notation. The bold, how do you do it on the board? It just doesn't make sense to me. But anyway. So this first test is the test of closure under addition, and that says that if U and V are in the set U, which is the subset that we're testing to see if it's a subspace, then U plus V is also a member of U. Okay, capital U is some subset of some vector space, and we want to know if it's a subspace. Well, if you take two things and you add them together, and you get something else that's in U as well, then so far so good. It looks like it might well be a subspace. The second test is what we call closure under scalar multiplication. And that is if some object U is in capital U and C is a real number, then C times U is also in the set capital U. And that's called closure under scalar multiplication. And if those two tests are satisfied, then the subset U is a subspace. Easy. Maybe. And something that I always tell my students is that all maths is easy if you know how to do it. And if you don't know how to do it, then it's hard. So learning new maths is always hard. Don't worry about that. Maybe you should worry a little bit because it means you're going to have to put some time and effort in. But that's normal for learning new maths. The third test that we're going to look at is actually a test for a subset to not be a subspace. If the zero vector, or what other object, so maybe it's a zero matrix, maybe it's a zero polynomial. If the zero vector is not in the set U, then U cannot be a subspace. So if the set fails this test, it can't be a subspace, but if it passes this test, maybe it is, maybe it isn't. We don't know. That's all going to depend on whether it passes the first two tests. So this is basically a quick and dirty test for something to not be a subspace. If it fails this, you've proved that it's not a subspace. If it passes this, you haven't proved anything, unfortunately. Okay, let's take a look at a few examples. The set of vectors in R4 form a vector space, and hence a subset of these vectors may or may not form a subspace. Suppose that S, being the set of all vectors of the form S naught T negative S, where S and T are real numbers, is some subset of R4. Then we want to apply the two tests to see if this is a subspace. Okay, let's take two vectors U and V. I've called this one S naught T negative S, X naught Y and negative X. And of course, those are all real numbers. Why did I pick those? Convenience. I could have easily gone A, B, negative A, C, D, negative C, anything. You can call them Fred and Wilma and Barney and Betty for all I care. It's not very convenient, particularly to write, but you could do it. Pick some simple letters. And they're real numbers. So let's do the first test. What is U plus V? It's this vector here, plus this vector, and we get this. S plus X, naught, T plus Y, negative S take X, and of course, I've written that and I've bracketed everything to make it really, really clear. We've got S plus X, naught, T plus Y, negative S plus X. And so we've got a zero in there. The last item is the negative of this, and this is just some real number, and so is this. So it's clearly in the set S. So it passes the first test with flying colors. What about the second test? Let's consider C times U. So we've got C times this vector here. That's CS naught CT negative CS. Well, CS is a real number, and this is the negative of CS. CT is a real number, and we've got 0 in the second spot. So that is also clearly in S. So it passes the second test, and therefore it must be a subspace. Passes tests 1 and 2, must be a subspace. Excuse me, which is very nice. Let's have a look at the second one. The set of all 2 by 2 matrices is a vector space. Now you have to be adding the matrices, you're not multiplying them, but that's okay. Any subset of this space might be a subspace. So let's suppose that T is the set of 2 by 2 matrices of the form A, 0, 0, and negative 2A, where A is in R. It's a real number. So let's apply the two tests. This time I've got capitals for matrices, not lowercase with twiddly things under them for vectors. I've got U and V, and they are both clearly of that form. So I'm finding U plus V, this one plus this one, which is equal to this. And hey presto, that's A plus B naught naught negative 2A plus B. That's clearly in T. I've got 2 zeros here, check, check. This here is minus 2 times this one. Yeah, passes that. So it's closed under addition, which is the first test. What about closure under scalar multiplication? What is C times U? It is C times A naught naught minus 2A. And we get that. And I've bracketed AC down here. That's clearly of this form up here. So very nice. That passes the second test as well. Must be a subspace. Let's have a look at one that fails to be a subspace. How about S equals the set A squared, which is a subset of R2. So it's potentially a subspace in R2. A is a real number, of course. We're going to try both tests here, even though one failed test is enough. So if your subset fails one of the tests, you can stop instantly. It's not a subspace. But just for practice, we're going to do both tests today. So we'll start off by testing the addition law. Let U be A and A squared, V be B and B squared. Okay, U plus V is this plus this, and that is A plus B, A squared plus B. But A squared plus B is not equal to A plus B squared, not for all A and B. You could find some special cases such as A equals 0, B equals 1, for which it would be true, but it's got to be true for all A and B, and that is not true for all A and B. Also note that C times, so it fails that test and it cannot be a subspace. So we could stop there, but we're going to go on and we'll do one more test just for practice. C times U is equal to C times AA squared, which is CA and CA squared. But CA squared is not equal to CA squared in general. This term here is not the square of this usually. Again, special cases, C equals 0 and 1, yes, or maybe A equals 0. But it's got to be true for all C and all A, and it isn't. So it fails the second test, and either of those failed tests would be enough to say, this is not a subspace. So we would normally not do both tests unless the first test passed. Okay, let's have a look at the last example, example 4. How about this set S, S1 negative S, which is a subset of R3. S is a real number. Subset of R3, maybe it is a subspace. But it does not contain the zero vector, since it's impossible for the middle component, which is 1, to ever be 0. And so this set fails to be a subspace. As soon as it fails to have the zero vector or object in it, you know it's not a subspace. Bam. So there we go. That's the two tests for testing for a subset to be a subspace. You've got to start with the vector space, like R2, R3, all the 2 by 2 matrices, all polynomials of degree less than or equal to 3, stuff like that. And then if you take a specific subset and you apply the two tests, you might in fact find that you've got a subspace. I generally don't do this third test unless I've got something in there that's a constant, because that's when it's likely to actually fail that test miserably. Anyway, I hope that's been handy. Again, if you found that useful, leave a comment, say hello, maybe tell us where you're studying and what you're studying. And yes, if you leave a request, one day I might be able to get around to it. So, but for now, I'll probably mainly do stuff based on my teaching. Okay, enjoy, and I hope you learn lots about maths and continue your studies and go on to have a great career. All right, bye for now.